Okay, so we're going to look at LC16 here. And the problem says, Bob is trying to show that a certain limit is equal to a certain value, which is not true. And let's see, let me confirm. Let's see, x is 1, y is 0. Yeah, so it's not true. So we just need to show it's not true by finding an appropriate value of delta that makes it show that the definition is not satisfied. The way we're going to do that is just like what we did in this previous problem, LC3. And let me talk you through that one. So in that previous problem, the picture looks like, so f of x was x squared. We were approaching 1, and we know that the actual limit is 1, but we were trying to show that the limit was equal to 3, which is wildly wrong, of course. So how do we show that that's wrong? Well, what has to happen is there. Let's see here. Am I looking at the right thing? Yeah. What I need to do is find a value of epsilon that shows that the limit can't work. The definition of limit can't work. So, for example, I could just pick a small little. What if I picked an epsilon like this, so that epsilon is about that big? Then I claim that there's no way that this could be the limit, because no matter how small of a little interval around here is picked, there's going to be values that land here that's very clearly not in that interval. Okay. So now the problem says, so clearly we can do that. Clearly we just choose a small epsilon, but the problem says how small does epsilon need to be? In other words, what's really the smallest epsilon that I can pick? If I pick an epsilon that's too big, the argument doesn't work. I mean, if I were to pick epsilon to be, a great big gigantic interval like this, then yeah, some little small interval, some little delta interval, have all the values of x will land inside of this great big monstrous interval that I've got here. So this is too big to work. This is smaller than necessary, and the question is, where's the cutoff? What's the smallest that it sort of can get away with being, or what's the biggest that it can get away with being? I mean, yeah. And I would like to propose that the switch happens when you sort of get to this point here, right? I mean, if your interval is small enough that it doesn't include points around here, then yeah, it does the job. It proves that this is not the limit. This value here is not the limit. But if it's big enough that it includes 1, it doesn't do the job, right? So roughly speaking, then the idea is that this is sort of the cutoff value. That's the biggest epsilon. All right? Yeah.
Is that an open or a closed interval?
Great question. So we have to worry about that a little bit. So let's consider what happens when epsilon is equal to 2. If epsilon is equal to 2, then we need to ask, for this interval, and I didn't leave myself enough space, but there's another up here. There's the sort of the upper end, and this here is definitely an open interval. That's the rule, right? So for that epsilon equals to 2, is there some little interval over here? And I claim that nope, there really isn't, because no matter how small this interval is over here, there's going to be some value on the left-hand side of 1, therefore smaller than 1. Its square is going to also be smaller than 1, and it falls outside of this interval. So epsilon equals to 2 works, right? So in LC3, let's see here. So in LC3, epsilon can be anything less than or equal to 2. Now, why did it end up being less than or equal? Why are we allowing this epsilon equal to 2? Well, because of the nature of this function. This particular function happens to be such that when epsilon is equal to 2, the argument still works. We still prove that this is not the limit. Epsilon equals to 2, it gives us the same effective conclusion as if epsilon had equal to 1, or to a half, or to a billionth. Right? So it happens to be. But if the function had been different, and I think there's an example, another exercise in here where the function is a different nature, and where epsilon equal to 2, where that's sort of the critical case there, actually doesn't work. That's depends on the shape of this function. So it's not always going to be a less than or equal here. Okay, so that's number 3. Let me go. Yeah. Mm-hmm.
What computations do you do to get that? How would you say it?
Epsilon.
Is equal to 2?
Well, yeah. So the idea was I was thinking about how the definition of a limit works, and if I have what I'll casually call a sufficiently small interval here around 3, then there is no way that I can make an interval over here whose values all land in this little interval around 3, because this interval around 3 is nowhere near where the actual value is going to be landing. Around 1, the values of the function are going to be landing somewhere in this vicinity here. So small intervals like that will not include all of those values. So the question is, how big can it get? And I just have to sort of keep making it bigger and bigger. And I can sort of tell that once I get beyond 2, once I've got intervals that are this huge, well, that's a huge interval around the number 3. I mean, the center of this interval here, the massive interval here that goes all the way, and that really does contain all the values of the function sort of around 1, because they all land sort of around here. So this is too big. This is smaller than necessary, and the sort of cutoff value is when the endpoint, so the lower endpoint of the interval centered at 3 is at 1, and the distance from 3 to 1 is 2.
Is 2 just a random place?
I'm sorry?
Did you just randomly pick 2?
No. The point is that 2 is the distance from the would-be limit, the claimed but false limit, and the actual limit.
Is it given in the question? Because they didn't give it, right?
Yeah.
How did you give it?
Yeah, look. So Bob's trying to show that the limit's equal to 3, but we know that this limit is actually equal to 1.
Right.
So it's the difference there. So, it's not, the 2 is not given. You have to figure it out. But I'm saying we figure it out from the fact that this is what Bob's trying to do. This is what Bob should have done. And so it's the difference that's relevant to the problem here. Yeah. Does that make sense?
Yeah. I felt like we're not supposed to assume that we know how to find the limit by plugging in when x.
Well, yeah, we're not doing any epsilon delta proofs here. All we're doing is we're concluding from we're making taking an understanding of what the definition is saying and making an interpretation in a specific case. Epsilon delta proofs are more sophisticated things where you have to go through an argument and say, suppose you have some arbitrary epsilon, then we're going to choose a delta according to the following formula and go through and do algebra and prove that a certain thing happens as a generality, that it always works. Here we're just plugging in just specific numbers. Yes. Okay. So yes.
Epsilon is a radius of the interval?
Yeah, that's right. Mm-hmm. Yep. It's a radius. That's right. Okay, so that's 273. That's LC3. Let me go on and do the next problem now, and the numbering is different here. So this is LC16 now, and I'll just do this part as part of the same recording. Let's see here. There we go. So LC16. It's a similar situation. We've got a function. Bob's trying to show the limit's equal to a certain value. Again, Bob has blown it and has the wrong value. And we want to know, again, what sort of epsilons can I choose to make this, to show that Bob's wrong? And it needs to be a sufficiently small epsilon. If epsilon is too big, it fails, just like in this picture. If epsilon is not big, and if epsilon is small enough, then it works. And the question is, what's that critical value? What's the biggest that it can be and still work? So we just have a little bit more trouble drawing this picture. And let's see here. What I'm going to do, let me just do this. So we've got a domain over here like this. That's the domain now. And we're approaching the point 1, 0. And the value of the function there, I know, and I can just plug in if x is 1 and y is 0, value of the function is -2. So I know that, you know, in the vicinity of this point, you know, sort of nearby that point, the values are going to be actually kind of landing sort of around in this general vicinity in here. Right? But Bob is trying to show that the limit is equal to 3. Because Bob has miscalculated or doesn't understand limits or something along those lines. Okay. So how big of an interval do we have to pick? Well, clearly a little teeny tiny little interval is going to work just fine. If you pick a teensy tiny epsilon, again, that's the radius. Epsilon is the radius of that interval. If you pick a teensy tiny epsilon, then sure, no matter how small this is, the values are going to be in this general vicinity and therefore not in this interval. But again, we also have the ability, we can sort of blow this. We can choose our epsilon to be too big, and if I choose my epsilon to be like way big, like, you know, 7 or what have you here, then yeah, the little values in there really are going to fall inside of my, you know, my great big interval here. So the cutoff, sort of the critical size, I can't draw the other end over here, but that critical radius, again, is going to be 5. It's the difference between the value that he thinks is the limit versus the value that actually is the limit. Does that make sense to everybody? Did you ever see how that's a lot like the previous problem? The sort of, this is a single variable version, and this is the same kind of thing. It's just that here we do the graph because that was convenient. But this it's a question of, you know, there's plenty too small, and then there's just barely small enough, and then there's too big. That doesn't work. Yes.
Okay, so the epsilon, and how are the epsilon and the delta related, if at all?
Well, yeah, no, it depends.
Do they have a direct relationship?
They not always. I mean, it depends on the nature of the function. So in this case over here, let's look at the single variable case. I claim that roughly speaking, and this is not entirely accurate, but roughly speaking, it's based on kind of the slope there, because, you know, you can view sort of a change in the delta interval. You can view as kind of a change in the x's, allowable range of changes of x's, and there's going to be a corresponding allowable range of changes of y. And so, when you have the right limit picked, then epsilon and delta roughly you sort of expect to relate by approximately the derivative. And that's not always true exactly, and sometimes you have to modify it a little bit because the function's curved and weird stuff like that. But yeah, but it's not always going to work out quite like that. And in the multivariable case, it's a little bit harder to see what exactly, if we had picked the right limit, what exactly is the relationship between the epsilon and the delta. It can be a little hard. Yeah.
Okay, and in terms of wording, how small does epsilon need to be? So
yeah.
The small size, the first example, for instance, is 2.
Yeah, that's right. So the answer to the previous question up here.
Is that the largest size or the smallest size?
That's the largest allowable size. So epsilon has to be 2 or smaller.
Oh, okay.
In this in the LC3. So it has to be less than or equal to 2 is the answer to that first problem. And in the second one, it's less than or equal to 5.
Just because the difference between the actual limit and
the yeah, that's right. Yep. Okay, let me stop this recording.